I've been telling everyone several times, because as we solve the question several times over the semester, right, we notice that when we use Gauss law, when we talk about Gauss law or Coulomb's law or things like that, when we want to find the charge or electric field or potential, it's always the same few objects, right? Straight line, this kind of thing. So if you know how to do that, then it should be good enough. Yeah, it's more or less that kind of thing. Basically, you need to know how to find the familiar with the the charge per length or charge per area, and then familiar with Kirchhoff's law, familiar with yeah, so all the things that we've been talking about. What else? Yeah, Coulomb's law, Kirchhoff's law, currents, capacitors. What happens when you put a dielectric in between a capacitor? Yeah, so basically, that kind of things. Exam time 4 to 6, correct. Yes, correct. Chapters 1 to 4. Yeah. So the thing that we will discuss today will not be covered in the exam, but obviously everything will be covered in the finals. So Thursday, it will be on Thursday. Thursday 4 to 6. 4 to 6 with you will see that the deadline is 6:30 p.m. right? That is the buffer time that how to say the buffer time for you guys to scan your solution and create your PDF file, prepare your PDF files. Yeah, it's this week, right? I've been sending reminders and announcements, so I should probably do that more often. Okay. So any other question about the exam? Yeah, so most of you guys took the course with me last semester. It's gonna be the same. So oh yeah, so Zhenlong, yeah, we have our midterm exam this Thursday. So some of you are taking both courses, right? You have two exams on the same day, unfortunately. But yeah, but it was, as you know, right, it was hard for us to schedule the classes. But you didn't miss much. I'm just reminding everyone that we have a midterm exam this Thursday. So this Thursday 4 to 6 p.m. And yeah, the chapter is from chapters 1 to 4. And then just to assure everyone that yeah, if you are familiar with the topics, if you know how to solve the examples, yes, basically correct. Yeah, Kahing. So no need camera for now. Yeah, so I do not get, yeah, so right now no need camera. Just I want to do it the same way as we did last semester. No need camera, but at least log into Teams so that I can give you guys announcements. Okay, so no need camera, but log into Teams so that I know everyone is online and can give announcements. Okay. Yeah, so that's it about the exam, I guess. Yep. Okay. Am I running test? My sound level test. Yep, I'm recording here. Yep. Okay, so so that is for Thursday, but for now we have to continue our syllabus. We have to talk about chapter 5, right? So chapter 5, continuing chapter 5, it's not in the exam, it's not in this week's exam, but definitely everything will be in the final, right? Doesn't mean we don't have to learn it. So we have to talk about current loops in magnetic fields. Why are they important? So let me mention a few things first. Right, from the point of view of physics, current loop is an important object to study in terms of electromagnetism. So let me write down first, current loops in magnetic fields. So having some magnetic field, right, are important because Okay, so there's one obvious reason, right? We are talking about current loops, and all the DC circuits, all they are existing in several loops, right? Kirchhoff loop rule, for example. So circuits consist of loops. So that is an important obvious reason, right? So if you put a electrical circuit in a magnetic field, it's gonna experience, it is a loop in a magnetic field. So when there is a loop in a magnetic field, what is going to happen? We have learned how to calculate the forces on the loops already, right? So if it's a loop, then we will see what's going to happen later. But right now, I'm just emphasizing why they are important, okay? And then, right, so because if you put a wire in a magnetic field, it will experience a force. This is one way to create a mechanical motor, the motor device, right? So that is one useful thing, electric motor. They are created using wire loops in magnetic field, right? So any electrical device that causes motion, like your blender or your stirrer, you know, in the kitchen, or even the ceiling fan, right? So the ceiling fan behind me is, you turn on the electricity, you use it to turn some object, right? Your washing machine, that kind of thing. And the reason is because we are turning on a current loop and having some magnet somewhere. So this magnet will cause it to move, right? So we are actually converting electrical energy into rotational kinetic energy. It's gonna rotate, right? So this thing is rotating right now, right? So that is is drawing electricity that's right now to convert electrical potential energy into rotational kinetic energy. So that's how this thing works, right? So that is the basic principle of many engineering equipments. Okay, so there is a third reason. Which one? I mean, it depends on the situation, right? So if you want to use cross product, you can even use right hand rule, or you can use, in our previous example, we use the IJK, right? And it actually depends on personal taste, because it just see which one you prefer, right? The answer is gonna be the same. So yeah, which method, like I would say, who cares, right? It's kind of your personal taste. So for me, you see, my habit most of the time is I use the IJK formula because it's easy to remember, right? The IJK list of this what I'm talking about is, you remember this, right? IJ cross K. So you just need to remember this one thing, and then the rest you can create quickly, right? So K cross I equals to J, and then reverse the order. But sometimes, right? Sometimes the question is just looking for magnitude. So for example, the current loop, right? I did not use IJK because I just look at some direction and then use the right hand rule and then say the direction and get the magnitude. That is fine. So that is get the magnitude. So you UV sine theta, right? That get the magnitude first, and then you figure out the direction later. That is also fine, right? So it's up to you, right? So that's why we have been using many different methods, so that you can use whatever method that is suitable. Yeah, I have been posting this the exam announcement in Teams, right? Yeah. So yeah, so it's up to you. See which one you prefer. Okay. If you have the textbook, right, the Young and Friedman, they prefer to get the magnitude first and then get the direction later, right? So I have been using IJK, but sometimes I use the other method. It kind of depends. On the question, and whichever is more convenient. So yeah, right. So for cross product, it is important to familiarize yourself with different methods for cross product, especially when it comes to magnetic field, because magnetic field, everything is like in loops, in circuits, right hand rule, and that kind of thing, right? So back to this, why is current loop important? We have a third reason that is, at least to me, that is the most interesting, is that when we talk about quantum mechanics of particles, then that is where it's becoming important. So I would say that elementary particles spin I'm not sure if you are learning this in modern physics yet or maybe in the future, but every particle has something called spin, right? And we can model this as tiny current loops. So that is one important aspect of current loops in magnetic field. So wait, I forgot my black pen. Hang on. So what is happening here with the current loops, right, is that, okay, so I have some circuit that is going in one loop, okay? So by using the right hand rule, my magnetic field is probably something along this direction, right? So going into the loop and going out to the loop, going like a magnetic field. So if you draw a tiny loop, right, right, the magnetic field is actually, it becomes something like a magnet. Sorry, hang on. Right, so it is going to be similar to the magnetic field of a magnet. Okay, so if you talk about elementary particles, right, if you take an electron, right, it has a spin because if you measure with very high precision magnetic field measurements, you can get a spin. So we normally draw the spin as an arrow because it's actually creating some kind of magnetic field that is similar to the to a magnetic field by a circular current loop, right? So we imagine that this electron is rotating as some kind of current loop because electron is a charge, right? So it has a spin. So a spin of a particle is going to be very, very important as you go on to quantum mechanics kinds of things, right? And because it is fundamental to quantum mechanics, and quantum mechanics is fundamental to every branch of physics, then it's going to be important everywhere else. Okay, so the spin of a particle is going to be important later on. So that is why I'm trying to convince you that current loops is an important thing to study. But right now we just treat this as this one is a bit too abstract and advanced, right? But we are still going back to things as a circuit existing in a loop, right? So what we are discussing next is just a simple description. So 5.4.1, we will be talking about the force and torque on a current loop. Okay, so yeah, right, so force and torque on a current loop. So what we have here is I will draw a three-dimensional picture, so it's going to be kind of difficult, but let's say I have a square wire frame, something like this. Okay, so this is in 3D, so so I will draw my axis to be, so this is my z-axis, this is my x-axis, and then my y-axis is going into the page like this, right? So it is making some angle phi with respect to the horizontal x-axis, and then this is a square frame wire loop where the length of this is, the sides of this is A and this side is B. Okay, so the current is going in this direction, right? And we are talking about current loops in a magnetic field, so this whole thing is existing inside a uniform magnetic field with some magnitude B, and the direction is upwards in the K direction. Okay, so so how do I calculate the net force acting on this current loop? Well, I have 4 sections of the wire, so let me call this section 1, and then section 2, this is section 3, and then this is section 4. Okay, so 1 and 2 are parallel to the y-axis, 3 and 4 are in the xz plane. Okay, so let us find the force on wire 1. Okay, so how to find the force on wire 1? So my wire 1 is over here, right? And how, remember the equation to get the force acting on the wire. So F is equals to I, and then the current direction vector, and then IL cross B. Am I right? So we just need to figure out what is IL and what is B. So B, we know this already, right? And then we just need to get the IL. So how to get the IL? The IL in this case is IL, well, it is a current of magnitude I, and the L is going in along the y-axis. So it is just the length of this wire. L is just A, and then the direction is J direction, right? So this is IL. Okay, therefore the force on this piece is just according to the Lorentz formula, IL cross B, right? So IL is IAJ, and then B is just BK. So what I have here is IAB J cross K, right? So you see, this is my personal taste, right? I like to write everything in terms of IJK, because now that I got J cross K, I just need to look at this. J cross K, it will give me a I. So this is I. So that means the force acting on wire 1, the magnitude is the current times the length of that piece times the strength of the magnetic field, and is going in the I direction. So this piece of wire is experiencing a force acting in this direction. Okay, so that is the force on wire 1, right? So everything is clear so far? The induced magnetic field, oh, not yet. You mean the FBI, right? The current, that yeah, so I'm going to talk about this after. We are going to finish, this is the last topic of this chapter. Once we finish this, we will go to the next chapter, then we do this, the Biot Savarts law, right? Is that what you're thinking of? Okay, so Biot Savarts law, also the grip right hand rule, but everything here is kind of like related to the right hand rule already, right? So this is the force on wire 1, and then now let's look at the wire 2. Okay, so let's look at wire 2. So wire 2, what is my IL for the case of wire 2? So my current is still I, right? The length is still A. The direction is now minus J, right? So it's minus IAJ. Okay, and magnetic field is the same. So the force on wire 2 is minus IAJ, and then cross product with BK. So it's just negative IAB in the I direction. So it's exactly the negative of this, right? And then for the case of this and this, I will not calculate because the forces on this will cancel out, right? Because the IL cross B, it will give me this direction, and this will give me this direction. So this is F4, this is F4. So these two will have the same force pulling apart, but this one will experience this force pulling on F2 over here. Okay, so this part will not be important. I forgot to say, right, this one is pivoted at the axis on the middle. Okay, because I want to see the torque acting on it, right? So if this is attached to some kind of pivot, then this thing will experience the net linear force is 0, right? So F1, F2 is 0, but it will experience some torque in different directions. So let us calculate the torque on the loop. Okay. Why is it not J? Not I plus J, since it's not exactly straight down. What do you mean? Because for force 1, right? Force 1 we calculated is in the I direction. Force 2, J cross I. J cross, hang on. J cross K, this is K. Yeah, J cross K, so J cross K is I, but there's a minus sign, right? So I got the IA. So it's both of them are in the I direction. Okay, so both of them are in the I direction. Okay. So the linear force are 0 because they are exactly opposite to each other, but this one will experience a torque. Okay, so what's the torque? Let me draw now. I'm looking at this thing from this direction now. So if I look at it from this direction, this is going to be my x-axis. This is my z direction now. So my wire 2 is coming out towards what you're looking at, right? So it's here, and then it is attached to this part is wire 4, and then this part is wire 1 is coming out here, right? So let's say this wire is pivoted in the middle, and the angle with the x-axis is phi, as we said just now. and we have calculated that the force is F1 in this direction and the force here is F2 in this direction, right? So this length is B over 2. Remember how to calculate torque, right? So calculate torque, well, let's get the magnitude first. The torque on this side is going to be the force times the perpendicular distance, right? So this is B half sine phi. So this is F1 and then B over 2 sine phi. So this is the torque on this part over here, and F1 is something that we have calculated. This is the magnitude only, right? So this is IAB. So I got half IAB and then small b and then sine phi, right? So this is half I A times B and then B sine phi. Okay, so this is torque 1. How about torque number 2? So torque number 2, the magnitude first, right? So the magnitude first is F2 and then the perpendicular distance. So the perpendicular distance is also B half sine phi, and it seems like they are the same, so it's half IAB and then capital B sine phi, right? So this is torque number 2. So both are exerting some kind of clockwise force in clockwise torque acting on the loop. So both torques are clockwise. Right, so the net torque is what? So let's write the magnitude first. The magnitude is torque number 1 plus torque number 2. So both are half of this plus half of this, so you just get IAB sine phi, right? And the and then the direction is clockwise. So we kind of got this already, right? What's going on? Oh, part 3. Oh, you mean the wire 3 and wire 4? Because the wire 3 and wire 4, so they do not make the thing rotate, right? So if this is a rigid wire, they have two opposing forces, but these two will not cause it to rotate, right? Because my pivot is over here. Okay. So it doesn't contribute a torque into the system, right? So you imagine, right, this wire that is rotating this way, some square frame, but if you pull on the two opposite ends of the frame, it doesn't contribute rotation, right? Only the rotating part of the frame, if you push it, it will rotate, right? So if you push it, it will rotate, but if you push it at this part, you pull it, nothing's going to happen to the rotation. It will cancel out. Yeah, it will cancel out. So the angle phi is this, right? But if I want to calculate the force, if the force with this, so it's IL cross B is acting here, so it's 90 degrees. This force and this force is 90 degrees to each other, right? This magnetic field and this wire are not 90 degrees. It's not 90 degrees. It's another angle. Is theta, right? If you want to calculate IL cross B. Okay, so but the same thing happens the opposite side, right? The wire is here, then they cancel each other out. So if you pull it at two different directions, is the direction is not straight down, right? Is one is here and the other is here. Starting out, we call it having angle phi. Yeah, it's true, right? Yeah. So yeah, so 1 and 2 is always parallel to y. That is also true, and also what Kai-Xuan said is kind of not wrong also, because we have not said what is angle phi. So phi can be anything. It could be 0. It could be anything. So it works for any angle, right? So it works for any angle. You just need to plug in this formula here. So apparently, when the angle is initially 0, the torque is 0. But if the angle is some 10 degrees or something, then you get this torque, right? So yeah, just put in the number accordingly. Nothing special there. But you notice this, right? This is IAB sine phi. Okay, IA little b and big B. Okay, so yeah, so this one, right, we notice that the AB is actually the area A, the area of the loop. Okay, so this formula, right, it seems like I am taking a this looks like a magnitude of a cross product, right? Magnitude of a cross product between what vector? Well, B is one vector. IA, is there a vector associated to IA? Yes, especially A, right? A, I can make it an area vector. And then if I have two vectors and find a cross product, it seems to be this the formula. So what we have here is I can express in vector form the torque on the current loop is IA, right? So the area vector and then cross B. Okay, so now that we kind of like guessing what is going on here, let me draw the loop again. Okay, so this is the wire loop, and then we have when we have an area, we can define an area vector, right? So area vector is just the area of the thing and then the direction that is pointing. Okay, and then my magnetic field is over here. So I have two vectors, I can find the cross product, and this gives me exactly the torque on this thing over here. Okay, so now this area, right, is another important quantity. Current times area is something that we define as the magnetic dipole moment. And we will call this mu arrow IA, right? And this thing is the area vector of the loop. Okay, so once I have a current loop, right, and then I can figure out the area vector, then I can cross product with B, then it will experience a torque. So this thing will cause it to rotate. No, this direction, right? It will cause, if put this in a magnetic field, it will rotate. Okay. So now, and I think another way to interpret this, right? What happens between these two wires? The force is here, and then the force is here. The force is acting on the same plane, acting on the same plane of the area, right? So the perpendicular distance from the axis is going to be 0. So this will contribute a 0 torque. But this force, right, is one side higher, the other side is lower. So it's not balanced, right? So the wires 3 and 4, they are exactly on the surface acting this way, and the other is acting this way along the surface. So there's no rotating effect, right? Remember, for rotation, if one side is higher than the other side, then it will cause some kind of rotation because it's not balanced, right? It will cause a rotational action onto it. Okay, so yeah, in other words, yeah, back to this question, right? You shouldn't hate yourself because what is actually yeah, it is what we are talking about. It is the same thing we are talking about for any angle phi. Okay. So this, yeah, so that is the force of a current loop that you put in the magnetic field. And this dipole moment, right, we have calculated this by assuming it's a square, but actually we do not need to assume to be a square. So any closed circuit, any shape, has a magnetic moment. So I can draw a circle because that is sometimes the more common situation. right? So the area is I over here, then from here I can get the area vector, which is just the area and then times the direction, right? So the direction is this, and then from here I can calculate the magnetic dipole moment of this object. It's just the current that is passing through here, and then times with the area vector. Okay, so we have again defined it using circuits and the area, but the dipole moment, right, is actually true for other objects as well. For electron and the spin, it has a dipole moment. It has a dipole moment, even though you can't really measure the I and the area separately, because electron is a point particle. So what does it mean by the area of the loop, right? But even for those kind of objects, you still have a dipole moment. Okay, so it's actually a more fundamental quantity. It's a fundamental quantity, but the way we derive it is by using the square loop, because it's the simple system we have been learning so far, right? So it's making everyone easy to understand. But in the future, just keep in mind that the magnetic dipole moment is the object that is kind of fundamental for across various objects. Okay, so any question? Yeah, I guess, yeah, it is worth revising, because this type of thing, right, it actually looks like surprising and complicated the first time you see it, but after this, when you watch it again, when you see it again when you read it again the second time, is actually, oh yeah, it's nothing that complicated, right? Not to say not easy, but is in us. I'm trying to explain that it's the same way that if you watch a movie, right, before knowing the spoiler and after knowing the spoiler is a different experience. You know what I mean, right? So if you know the ending, then you can see, oh, this guy already said this at the beginning, right? So then you can all sort of keep track of everything that is happening towards the ending. That is the second time reading lecture notes, right? So the first time is like suddenly the plot twist happen, and then you're like, wow, what the hell, right? So that's the kind of thing. But once you watch a movie the second time, then you see, oh, they actually mentioned this at the beginning already, right? You just didn't notice it. So the same situation happens like when you take a class the first time and then you read again the second time. That is why you need to revise, you know. Yeah, Tenet or any of the Christopher Nolan movies. Yes, kind of. Yeah. But yeah, but the difference between physics is that you don't have to watch the whole movie, right? You just need to read the notes. Because if you are doing live class, there will be no videos. So you really need to read the notes. I guess Tenet is probably not a good example because Tenet is not what I'm talking about, right? It's whether you know the spoiler or not. Tenet is just a complicated story, but what I mean is like if you know the plot twist, the surprise ending at the end, right? So, but if you watch it the second time, you actually see at the beginning of the movie, the good movies lah, you know, like the secret bad guy actually say something that hints he is the bad guy. You just didn't notice it the first time, right? But when you watch it the second time, it's like, oh yeah, we know what he's doing. You know, so it's the same thing for this. So yeah, so don't be. That's why students are scared learning physics. So don't be scared if you see something very complicated. If you run through it the second time, you see what's going on. Okay. So yeah, before I waste too much time rambling about Tenet, let's calculate the work done on the loop as it rotates from, yeah, so again, right, like what Kaishan was saying, start some angle phi, yeah, it's for any angle. So let us say initially it has some angle phi 1 to some other angle phi 2. We don't need to specify exactly what is this angle, right? So it's true for what we have been calculating most of the time, right? When an object is experiencing a torque, let me remind you that the work done acting on it is you take the magnitude of the torque and then you integrate with respect to the angular displacement. So the angle here is representing the angular displacement going from phi1 to phi2. Okay, and we have calculated the torque here already, right? So which what we got was IAB, the magnetic field, and then sine phi d phi, and we have said that this is equals to I times area, which is the magnitude of the magnetic dipole moment. Okay, so the work done is just the magnetic dipole moment sine phi, integrate this with respect to d phi, going from phi1 to phi2. So if you perform the integration, you just get negative mu b cos phi from phi1 to phi2, right? And then you put in the limits. So what we have here is negative mu b cos phi2, and then plus mu b sine phi1. So this is something similar to what we did last time, right? When we want to calculate the work done of a conservative force, then you look at the antiderivative. We define the antiderivative to be the negative potential energy, right? So we are going to do the same. We are going to define the dipole potential energy so dipole potential energy to be some potential energy is negative mu b cos phi, right? So mu b cos phi, so that means the work done is just the potential energy at 2 minus potential energy at 1. So potential energy at angle 2 minus potential energy at angle 1. So this is the change in potential. Okay, so that is the work done, right? So if I have a dipole, right, a current loop in a magnetic field is having a potential energy, right, because it has a tendency to rotate in a certain direction because of the torque, right? So that is where we get the potential energy of the thing. And in fact, right, if you look at this one is like this is a magnitude of a vector, right? This is also a magnitude of a vector, and then this is the angle between these two vectors. So the angle between these two vectors, I forgot to draw over here. Where is it? Not very convenient, but yeah, it's the angle between the two vectors. So this is actually a dot product between mu and b. So the potential energy is equals to negative mu dot b. Okay, so that is the magnetic dipole moment. Okay, so any questions so far? You might have seen this before already. I don't know, when Prof Ong was teaching you thermodynamics, right? Did you guys calculate paramagnetism? Because if you're calculating paramagnetism, you did make use of this formula at some point, but at that stage you didn't really know it yet, right? So it's yeah. Yeah, unfortunately, like MCO, repeat and repeat. The loop as is the plane when calculating the moment. Yeah, yes. So the loop is a plane, right? So it's a plane and then having a certain angle. So it's like the area that we have been calculating. Yeah, right. You saw it. The formula was in assignment topics. Yeah. Yes. So sometimes yeah, because thermodynamics, the simplest example applying your partition function is the paramagnetism problem, right? But paramagnetism makes use of this formula. So maybe you have seen this formula at that time, but you don't know where it came from yet. So yeah, so this is where it came from. in statistical mechanics part. Yeah, like so I don't know whether he called it paramagnetism. The textbook, yeah, the textbook I use, it call it paramagnetism. Right, so it considers like many spins in some material, right, and then you put it in some external magnetic field. So the energy is the summation of, you know, the partition function is the summation of the beta of the energy, right? So the energy is going to be mu dot b. So if it's pointing parallel to the magnetic field, it will be minimizing the potential energy, right? Pointing the other direction will be maximizing the potential energy, right? So you see, right, because u is equal to mu b cos phi. So if cosine phi is 0, right? So if cosine phi is 0, so that means if my loop is pointing the same direction as my magnetic field, my potential energy is just negative mu b, right? But so my current is clockwise. So if my current is in the other direction, if my loop is pointing the opposite direction as my magnetic field, it has a higher potential energy. So when this is an important, I'm not just referring to thermodynamics anymore, it's important for us now, is that when your magnetic dipole moment is pointing the same way as your magnetic field, the potential energy is lower, right? So this one is having a higher potential energy, right? This is a lower potential energy. Then this is all the intermediate values of potential energy. So if I put a magnetic dipole, if it's freely rotate, right, as we have learned from since mechanics, if you just let go of a system, it will go to a situation with minimum potential energy. So if something that can, the circular loop, if it can freely rotate but I can let it go inside a magnetic field, it will just rotate until it will point in the same direction for the magnetic field, because that is where it is the minimum potential energy. Okay, so that is where this thing came from. So the connection to statistical mechanics is, statistical mechanics, you consider many loops, right? Many atoms inside a material. And in quantum mechanics, it is quantized. It's either pointing this way or pointing that way. Then you can actually calculate the energy. So if all the spins are pointing along the same direction, it will be the minimized potential energy of the system. Okay, so it will minimize the potential energy. Paramagnet, right? Okay, yeah, paramagnet. Yeah, so this thing, magnetic moment. So this is the total number of parallel direction plus the total number of minimum opposite directions. Yes, so that is the connection that we see there. Oh yeah, because Kaheng you didn't take, right? Yeah, don't worry. It's just to demonstrate that for whoever was taking thermodynamics, yeah, your efforts are not wasted, right? So these are interrelated. So and kind of important there as well. Another thing to mention is that so right now I have one loop, right? But for many electrical devices, you actually wrap the same wire around the circle many times. So that will create a coil. So a coil is if the loop consists of a coil looped around n times, then the magnetic moment is just multiplied by n. Okay, so that is pretty much it. Oh, yeah. So that's why, like, when I mention these kind of things, right? I'm trying to convince you guys, like, there is, regardless of like what notes we give you guys, you know, how me or Prof Ong teaches, there is some, you know, there is a physics underneath everything that we are talking about, right? because in physics and in math, right, our job is to understand how the universe works. Okay, so if you study a piece of magnet in a temperature T, you know this thing happens. And why? Because of electromagnetism. And why electromagnetism? Because of the Lorentz force law and all that kinds of things. So let's see an example. Right, so you have I got more details in these notes, but let's see an example. Right, so I have a circular coil. I have the radius, so I can get the area. Once I have the area, I can get the magnetic dipole moment. Right, so it's n equals to 30. So 30 turns of wire lies in a horizontal plane. It carries a counterclockwise current view from above with a current of 5 amps. So, oh yeah, I forgot to do this. It current 5 amps, and then the magnetic field is 1.2 Tesla directed towards the right. So find the magnetic moment and the torque on the coil, and then find the change in potential energy. So basically, yeah, what we were talking about just now, but with specific values to work out. So this is example 5.4.1. The radius is 0.05 meters, right? 30 coils, 30 turns of the coil. The current is 5 amps. The magnetic field magnitude is 1.20 Tesla. So what is happening here is that what did the question say again? So it just lies on the horizontal plane, right? So it lies on the horizontal plane. It did not define what is your xy axis, so you can define it for yourself, right? So if this is my x direction, if this is my y direction, right, and this is my z, and then my coil is in the horizontal plane. So my horizontal, I will say that my horizontal plane is the xy plane, and then the current, if I look down from above, it is anti-clockwise. So my magnetic dipole moment is just n, and the current and the area vector. Am I right? So number of loops is 30, 5 amps, and then the area now is pi r square, and my area vector is pointing in the k direction, right? So yeah, use the right hand rule. I think I forgot to say this. Yeah, use the right hand rule. So this is pointing in the k direction, right hand rule of the wire. Okay, so if you plug in the numbers, 30 pi, and then r square, and then 5 amps of current in the k. So this is 1.18 a meter square in the k direction. So this is the magnetic dipole moment. Right. So the magnetic field is directed towards the right. So the magnetic field directed towards the right. So that means, let's say it's pointing in the j direction. So it's B0 in the j direction. Then the torque is just mu cross B, right? So it's just Ni pi r square k cross with Bj. Okay, so it's perpendicular to each other. So what we have here is that Nib pi r square k cross j, right? And what was k cross j? K cross j was jk is I, so k cross j is minus I. So it's minus Nib pi r square in the I direction. So my torque is going to be in the this thing, right? So this is the torque acting on this. So it's gonna rotate with the x-axis in the I direction. So it's gonna rotate clockwise, I think. Yeah, clockwise. Okay. Then for part B, the coil rotates from initial orientation where it's parallel. What is the change in potential energy? So basically what is happening here is that my coil is initially, well, the initial my magnetic moment will depend on position because it depends on the orientation of the thing. So initially it is pointing like flat on a horizontal surface, so my magnetic dipole moment is pointing straight up. Okay, so it's n pi r square I in the k direction, and then later it is pointing parallel to the later my coil is pointing parallel to my x-axis, so it's n pi r square I and then the j direction, right? So I can calculate the potential energy at these two cases. So my potential energy at the first point is mu dot b, right? My b was pointing hang on. My b was pointing in the right direction. Oh yeah, j, right? So k dot j is going to be 0. I thought I made a mistake. But for this case, mu2 dot b is just minus n pi r square I, j dot product with b not j. So j dot j is just 1. So it's just minus n pi r square IB, right? So the change in potential energy is final energy minus initial energy. Initial energy was 0, so it's just pi r square NIB. So this is the change in potential energy, right? So it's kind of, so another reason why I like to do things in IJK is very systematic, right? Just follow the procedure, mu dot b, then you know I dot j, you know where everything is happening, right? And then you can calculate the values very quickly. So that is one advantage of determining this. Okay, so any question? Towards the right can put yes, so the vector b is I instead of j, yeah, because I claim that this is the right, but if you draw your x-axis on the other side, then yeah, because notice that your answer doesn't really matter, right? The direction, because your axis is something that you define, right? So I define my axis like this, so my right is here, but if your axis is this way, then your right is the j direction. So it should not depend on the choice. Yeah, actually, to be honest, every subject is difficult, right? Whether you, I mean, yeah, have you met a student that say that their own subject is easy? Like you go to engineering or you go to new energy student, no one will say their own subject is easy one, right? You talk to a TCM student or a journalism student, yeah, everyone will say their own subject is hard, right? Because nothing is going to be easy. Oh, so business people will say that, is it? Yeah, but business job is very stressful also. If you work in business, advertising even more stressful. Anyway, I think now is a time to take a break. So yeah, 10 minutes. So we come back at 3:05. Let's take a 10 minutes break. And then I can stop recording, and we continue chapter 6 after this. I start here too. Yeah, so let me recommend a book, the Gödel, Escher and Bach. Maybe if it's famous enough that most of you have heard this already. By Hofstadter. Yeah, this book. So if you are interested, this is a very interesting book. It won the Pulitzer Prize in 1981. Then it's like talking all the concepts about math, physics, and even biology, and also some music things, and it explore all kinds of interesting topics. And along the way, this book explain the Gödel's incompleteness theorem. But I think the math major will learn the Gödel's theorem in more detail than the rest of us, I'm sure. Right, so you guys will know more than me about this. So everything, most of the things I know, I gathered from that book and like other related things only. So what's the other one? I will click, since the internet is slow, I will just let it load. And meanwhile, we shall go to the next topic. So by the way, before I forget, right? So our exam will be same as what we did last time. So you can get the exam here. When the day comes, you will see this appearing, and this is where you download the exam. I have uploaded the solutions for the relevant tutorials already, and the quiz solution, if you have not noticed, is uploaded here already as well. Okay, so you can for studying, you can go there and check out those things. So yeah, like I said, I'm very bad at planning revision because I never know what to say other than repeating something I already know. No, but if you have question, you can message me a specific question that you're not sure, right? Then that is easier for me to do. Otherwise, I'll just repeat the same lecture about Coulomb's law. I also don't know what to do. Yeah, Coulomb's law again, Kirchhoff's law again, that kind of thing. The Gödel's what theorem? Gödel's theorem. So Gödel is this one you asked me earlier. Yeah, Gödel's incomplete theorem. No. There are some like students that dropped the course that I forgot to remove from the list. So everyone submitted. Yeah, don't worry. The rest is like they submit, but I still haven't deleted the names. So it's still like extra students left. So don't worry about it. Yeah. And also myself, I did not submit, so I'm one of them. So I'm one of them. I think it counts me also. If I'm familiar with the system. Okay, so now we go to a new topic. So this is where we are now talking about the sources of magnetic field. Notice that magnetic field chapter is kind of tricky, right? We took so long and we still haven't even studied how to calculate how is a magnetic field created. Everything that we've been doing so far is given a magnetic field first. We are calculating the effects on moving charges. So we have been spending time on the Lorentz force law, right? A moving charge will experience a force because of the magnetic field, and it causes it to go in a rotating circular motion kind of thing, right? And we do the same calculation for wires, and we just did it for the current loops. Okay, but how is a magnetic field created? So this is the question that we want to address in this chapter. And as always, right, obviously it's a bit more tricky compared to electric field, because electric field is very easy. Electric field, right, the sources of electric field is charges. Charges create electric field, right? So charges create electric field using the Coulomb's law, so 4 pi r square, right? So yeah, Coulomb's law or Gauss law, the electric field is because of the charges. So what is the thing that creates magnetic field? Okay, so it turns out that the answer is, well, we have no magnetic charges, right? There's no magnetic monopole, but what we do have is current. And we perform experiment, we realize that currents is the one that causes magnetic field. So what are currents? Current is basically just moving charges, right? So moving charges, currents. Okay, so currents are the one that creates the magnetic field, right? So current is I, right? Why is I? I is moving charges, right? If you remember, is NQ VDA, right? So we derived this in chapter 4, was it? Right? So charges that move will create the magnetic field. So that is our sources of magnetic field. And a simple experiment anyone can do is the following. Okay, so according to experiment, right, this is how this law was initially discovered. Current carrying wire well, firstly is the observation that a current carrying wire is you can attract a magnet, so affects magnets, right? So what you do is, like, let's say you put a current DC circuit over here, and then you can try this at home if you have some direct current battery kind of thing, right? If you put a compass nearby, right? So you put a compass, right? Compass. So if you bring a compass near to the wire, it will start to move the needle of the compass, because compass by right is always pointing to the North Pole, right? But if you bring a wire near to the compass, it starts to affect the motion of the compass. That means the wire is a source of some magnetic force that is acting on this magnet inside the compass. So that is the so that is the feature. That is the hint, right? That current is a source of magnetic field. Okay, so this is what we want to explore for today. Okay, so let's go to the first section, 6.1. Firstly, current is a bit later. We just consider what is the magnetic field created by a single moving charge, a point charge. So magnetic field created by moving point charge. So just one charge first, and then later, because a current is just many charges flowing in the same direction, so later we'll figure out for the case of the current. But for a moving point charge, how can we find the magnetic field? So firstly, let us consider a charge Q, right, moving at velocity v. Okay, and then at one instant we measure the magnetic field at a point P somewhere, right? So basically what is happening here is, what I'm saying is I have a charge that is moving at some velocity v, right? And then I want to calculate the magnetic field, right? But usually we are capable of determining the magnetic field at some position. So let's say this is point P, right? So at point P, what is the magnetic field over here? So this point is where we call P. So in order to calculate, right, I want to give you a law that is something similar to Coulomb's law. Similar, but it's a bit tricky. So let us define a few quantities first. So let me say that well, this part is similar to Coulomb's law. This is the distance between Q and P. So the distance from here to here is R. Okay, and then also kind of similar to Coulomb's law, the direction now will be important. So R, right, what is the direction from here to here is, this is a vector I will call R hat, right? R hat is just a unit vector, it's just to tell you the direction, right? This part will tell you the distance. So the R hat is the unit vector pointing from Q to P. Okay, so this is the unit vector pointing from Q to P. So this is the setup of our situation. But let us imagine, right, how did these people discover this law? Well, they move the charge here from here to here, and then they measure the strength of the magnetic field. So what was the result that they got? So yeah, let me just quickly mention what they got. So if my charge, if this is a positive charge, right? So if this is a positive charge and it's moving here, it turns out that what you get is that the experiment tells you that my magnetic field is pointing out of the plane. Okay, but if my moving charge is in the same place but moving in the opposite direction, so my V is going here, this is still a positive charge, then my magnetic field is in the opposite direction. Okay, and then the result will flip if I swap a positive charge to a negative charge. So now if I have the electron, so it's a negative charge but it's moving here, then it turns out that my magnetic field is going into the page. But if I change the direction for the electron, it is going out of the page. Okay, so it depends on the direction of V, and it depends on the sign of the charge, right? Whether the velocity is this way or that way, whether the charge is positive or negative. And then the reason why we define distance is because the strength of the magnetic field depends on the distance as well. So it turns out that the magnetic field is inversely proportional to r squared. So these are the experimental results. And once we collect all this observation, we have a formula to we infer a formula of the magnetic field created by the moving charge. So let me show you the formula now. So the formula is, what is the magnetic field? So then the magnetic field is, well, as I say, right, the magnitude is inversely proportional to r squared, and this direction will give you a direction into the page, out of the page, so it's perpendicular. So it has something to do with the cross product, and the answer is QV cross r hat. Okay, so QV cross r hat, and as you can see, right, QV cross r hat. So if you look at this example, my r hat is pointing this way, so V cross r hat is using the right hand rule. I get the magnetic field that is coming out of the page. But my V here, my r hat, if my V is in the opposite direction, right, so V cross r is, I'm getting the direction that is into the page, so that's why into the page. And then if I reverse the Q, I flip the direction. Okay, so similar thing to your Lorentz force law. Okay, so this is the relationship. It turns out that the higher the value of the charge, the stronger the magnetic field. Kind of makes sense. But this is the relation. But what is the constant of proportionality? The constant of proportionality is a fundamental physical constant. We call this mu over 4 pi. Right, so this mu is having the number of 4 pi times 10 to the minus 7 Tesla meter per ampere. Right, so this is what we call the permeability of vacuum. So this is the formula created by, this is the magnetic field created by the moving charge. Okay, so now we know the law. Am I recording? Yep. Okay, so any questions so far? Drett's law. Okay, so here is an example to see how things work. Let me bring this up as well. So two protons move parallel to the x-axis in opposite direction at the same speed, okay, shown in this figure. So one going to the right, one going to the left. At this instance shown, find the electric and magnetic forces on the upper proton. So it helps us save time. We just need to focus on this thing and find the magnitudes. Okay, so how do we figure this out? Well, let's draw the situation. Firstly, I have a proton that is positively charged and is moving here, so is moving in this direction, and the other one is positively charged and then this is moving here. So if I call this positive v, then the other one is minus v, right? So same speed but opposite directions. Okay, so I want to calculate what are the forces acting on this. Well, to get the forces, I need to know what is the electric field and what is the magnetic field. Electric field, easy, right? The distance is r, Coulomb's law. But what's the magnetic field? We need to get the magnetic field first before we know the force, right? So let's call this point P. Okay, and firstly I want to figure out the magnetic field at P created by this lower charge. Okay, so how do I find the magnetic field? Basically, I want to make use of this formula. So I need to know what are all these vectors. So my r hat vector is pointing this way. My v vector is pointing this way. So yeah, so again, right, the cross product is a personal taste, and my favorite way to do this is I want to write everything in terms of ijk. Okay, so this is y, and that means my velocity, now that I have defined my axis, is the speed times in the I direction, right? And then my r hat is just pointing along the y-axis, so that I know how to calculate the ijk, right? So my magnetic field is just mu over 4 pi, and then q is a positive charge, and then the v is just vi cross j, and then the distance is just some r square. So what we have here is mu qv over 4 pi, and then there's a r square, and then at the back is the cross product between vectors, so I cross j. So I cross j just gives you a k, so my magnetic field is pointing in the k direction, so it's mu qv over 4 pi r square in the k direction. Okay, so I got the magnetic field, and then the electric field P created by the lower charge is, what's the electric field? Very easy, right? The Coulomb's law. So q over 4 pi epsilon r square, and then the direction is r hat, but we have said that my r hat is the j, so it's just q over 4 pi epsilon r square in the j direction, right? So very simple, right? So the force, what's the force on the upper charge? Well, let's calculate the net force, right? So firstly, it is obviously the force because of the electric field plus the force due to the magnetic field. So the electric field is just, the upper charge is also having the same charge q, right? So it's just q times E, and then the magnetic force is using the Lorentz law, so it's qv cross B. Okay, so this force is just QE, so it's just q times this, so it's just q square over 4 pi epsilon r square in the j direction, and then plus qv cross B. So what's qv? Qv was q and then the velocity and then in the I direction, am I right? And then oh wait, I almost made a mistake. This is the upper charge, my v is pointing to the left, so it's negative, right? So it's negative, and then I cross with my magnetic field, so it's mu qv over 4 pi r square cross with the k direction. Correct? Yeah, yeah. Cringe. Page 6. Okay, so just need to simplify everything. So what we have here is quite simple for the Coulomb's law. So the force is just yeah, Coulomb's law, exactly. There's a minus, looks like there's a q square, there's a v square, so I got mu v square q square over 4 pi r squared. Okay, so this is the net force acting on this. In fact, I can factorize, right? So what we have here is, do I need to factorize? A bit lazy, but yeah, it's basically q squared over 4 pi r squared. So it is 1 over epsilon j minus mu v square k. So this is the force acting on the charge, right? So one is acting on the j direction, one is acting on the k direction. But what the question is asking for is actually the ratio, right? Find the electromagnetic force and then compare their magnitudes. So we found the electromagnetic force already. In fact, I already added up the two forces to get the net force. Now I want to compare the magnitude, right? So the magnitude is here and here. So let's find the ratio of the magnitudes. Okay, so ratio of the magnitude. Okay, so let's put what is the magnitude of magnetic force divided by the magnitude of the electric force. We will get something interesting as you will see later. So the magnetic force, let me just copy everything down and then we slowly simplify later. So the magnitude of this force is just mu over 4 pi r square, right? And then I'm dividing by the electric force, which is just Coulomb's law. So it's q square over 4 pi epsilon r square. So 4 pi r square cancel, q square and q square cancels with each other, and what we have here is mu v over 1 over epsilon. So the ratio is just as you can see, 1 over epsilon divide is just mu epsilon v square, right? So this is the ratio of the forces. Now maybe some of you already know this, but let me show you this number, right? So let's look at this number. This number is actually going to be very special, right? In particular, I will show you what is happening if I calculate 1 over square root mu times e. So who already knows the answer? You can spoil it in the chat. Let's see how many people know. Yeah, yes, speed of light. Yeah, that's interesting, right? Because let's calculate this combination. Okay, so what was mu? What was 4 pi? Mu was 4 pi times 10 to the 7, and then the epsilon is 8.85 times 10 to the minus 12, and then you take the square root. Right? So let's bring a calculator and see what happens. Okay, so what we have here is the 4 pi, right, times 10 to the minus 7 times 8.85 times 10 to the minus 12. So you got some number here, right, and then I take the square root and then I inverse this answer. I get exactly this. So this is actually exactly the speed of light, right? So this is actually 3.00 if you round off times 10 to the 8 meters per second. So this is actually the speed of light. So the ratio of these two, this actually what we have found is 1 over the speed of light square. So the ratio of these two forces is v square over c square. So that's pretty cool, right? So notice that nothing can travel faster than the speed of light. So only for particles traveling exactly at the speed of light, the magnetic force equals to the electric force. But of course, everything must be slower. So if everything must be slower, then this ratio must be smaller than 1. So in general, it turns out that the electric force between two same charges is usually stronger than the strength of the magnetic force of the same two charges. I cross k. Did I do I cross k? Oh, yeah, you're right. I cross k. Yeah, I cross k. So it's I cross k. And what was I cross k? So This is very handy, right? I cross k is minus j. So this is minus j. So both are pointing in the j direction. Let me double check. I mean, the answer is in the notes. So is it correct? Yeah, both are pointing in the positive j direction. Correct, correct. Yeah, so I'll explain why, but v square is fb, not really, right? Because what we have here is that it's not v square equals to b, it's the ratio. The ratio of these two is the ratio of these two, right? Because we never say fe is c squared, right? We are not saying that this is equal to this, this is equal to this, but the ratio is equal to this ratio. So that's all it's saying, right? So you see, like somehow it has something to do with the speed of light, and it's actually not that surprising because the original reason why Einstein discovered special relativity in the first place was he was studying electromagnetism. Yeah, because his original paper, when he started to discuss about special relativity, right? The paper where he derived the E equals mc squared was titled "On the Electrodynamics of Moving Bodies." So electrodynamics is another word for electromagnetism. So sometimes we call it electrodynamics. Is a more general term because it includes dynamics, right? Yeah, so anyway, you will see this formula pop up quite often, and the important formula we will derive later in chapter 9 is that the speed of light is actually 1 over mu epsilon. Okay, so yeah, so that is one discovery. That is the discovery of special relativity is very closely tied to electromagnetism, and the realization that this equation is true has the implication of like relativity, you know, the speed of light is the same in every frame, all that kind of thing. Okay, so yeah, interesting stuff, right? At least to me. So yeah, so all these are interconnected in one way or another. Another reason is because we will learn later in the future that, you know, remember Lorentz transformation, right? The equations of electromagnetism are unaffected by Lorentz transformation, so it respects the symmetry of special relativity. So, you know, when we did relativity, right, once we discover special relativity, we discover the Lorentz transformation, we discover time dilation and length contraction, then we need to go back to modify Newton's law, right? Remember, we had to do that. We need to define relativistic momentum, that kind of thing. That's the reason is because Newton's law is not invariant under Lorentz transformation. But then electromagnetism is special because after we discover special relativity, right, we don't need to modify electromagnetism. It remains the same. So because the electromagnetic equation is already satisfying special relativity, and that is how Einstein discovered special relativity, because he looked at special relativity. Why is it so consistent? It's more consistent compared to Newton's law, right? If it respects the speed of light and all these kind of things. So from there he looked at it, and then he discovered this, and then we go back to modify Newton's law, and now we realize Newton's law is only true for velocity much slower than the speed of light. But otherwise, yeah, we can't. For close to speed of light, we cannot use Newton's law. But for electromagnetism, it's special. Electromagnetism, fast moving velocity still works. That is the why electromagnetism is kind of powerful in that sense. Okay, so that's the other thing. The next thing is Biot Savarts law. Yeah, magic. Interesting, right? Yeah, I also find it fascinating too. That's why like electromagnetism is one of the most interesting topics. You can always find interesting connections to almost every other branch in physics, right? Even in this class alone, we connected to statistics, your thermodynamics, paramagnetism. Now suddenly we went to relativity. So it's like very fundamental, and it's very important, you know, in explaining many things in physics. So why it's hard to, I think it's by accident. Okay, firstly, why is it already satisfying? I think the reason is kind of by accident, you know. So when later we will derive the Maxwell's 4 equations, and then we got a set of equation, then yeah, that equation explains our Biot Savarts law, electric field, magnetic field, everything. Why does it satisfy? I don't know. It's like once we derive it, it is something that we realize later, and then it's already satisfying special relativity without people realizing it at first. Until Einstein, he realized that, oh yeah, this thing is consistent. So why is hard to say why, because it satisfied by accident without they didn't do it on purpose. Yeah, so that is one stupid reason. And also your other question, am I going to teach QM? One of these two. I think we are not sure yet. Depends on timetable and all these other things, you know. Yeah, QM or theoretical mechanics. Not sure yet. But so yeah, so in any case, right now, before we are able to reach Maxwell equation, we need to learn along the way is that the Biot Savarts law. So Biot Savarts law is to generalize what we have been studying so far, because we have been studying what is the magnetic field created by a single charge. Biot Savarts law is to find the magnetic field created by a wire. So a wire is just many charges flowing, right? So how do we make sure this works? Well, first thing we notice is we need to point out that the magnetic field, like the electric field, it also obeys the superposition principle. Okay, so let's say superposition principle is like if I have one charge going at this velocity, right, and then what is the magnetic field created at point P, right, and then if I have another charge moving at another velocity, so the distance is a bit different now, the direction is also a bit different, so it's going to create another magnetic field, right? So electric field we know, so the electric field is the electric field created by charge 1 plus the electric field created by charge 2. We know this already, but it turns out that the same thing is true for magnetic field as well. Okay, so magnetic field is magnetic field because of charge 1 plus magnetic field because of charge 2, right? So it's just mu over 4 pi, right? So I got Q1 V1 cross the R1 over this direction, and then same thing for the other two. So we just need to substitute the corresponding values for the second charge, and then you just add up the two vectors, then you get the total vector, right? So this is the superposition principle for the magnetic field. So once this one is pretty easy to convince ourselves. So then the next step is just, if this is charges moving in the current, then the magnetic field is just the sum of all the charges flowing inside the current, right? So for a current carrying wire, I'm recording, right? I'm recording. Yeah. Yes, science always come from accident. Yeah. Like the penicillin was also discovered by accident, right? Teachers, the harder one. Well, it is subjective. Which one is harder? So yeah, both are, yeah. Which one is harder is a subjective question, because some people will say QM is hard, some people say mechanics is harder. Yeah, so now for two charges, the field is this. So then we just look at many charges. So this will become a wire. So current carrying wire right is basically consists of many moving charges. Right, so if I have a wire, so we have derived the motion of charges inside a wire in chapter 4 already, right? For example, if my charge carrier is Q, then it is moving under some drift velocity Vd, right? So if I zoom out, right, so what I'm going to have is, well, everyone here is inside a wire moving with current I. Okay, so what we do is, okay, if I chop this out into many pieces, this is an infinitesimal part, right? So I want to calculate what is the magnetic field created at point P, right? So what is my magnetic field over here? So we look at the infinitesimal segment. So the infinitesimal segment and then the length is dl, so I got dl over here, right? In fact, we have the idl vector, right? So idl vector is just the magnitude of the current, the direction, and then the actual length itself. Okay, and what was I? I is, if you remember our chapter 4, which you should, because it's going to be like exam is chapter 4, right? NQ, V, D, N direction, and then the dl. So this part, we recognize that this is our Vd, the drift velocity. Right? So we conclude that my IDL is just N charge carrier A, and then the drift velocity, and then the dl. Okay, so what I'm going to do is, I want to use the Biot Savarts law, right? So Biot Savarts law is to say that my F is my magnetic field is mu over 4 pi, and then the charge, and then cross the r direction, and then r square, right? So I want to know what is the total charge and the total V, right? So I will split the V outside, so I got IDL, and then this is equals to NQA dl, and then this is V, right? So again, we're recalling from what we know from chapter 4, this is the net charge inside the segment, right? So it is having some value of net charge dq, so I'm going to call this dq. Okay, so at the end of the day, right, so these are details, right? So if you're confused, again, you read the second time once you know the spoiler. But what I want, the formula that I really want is dq and then v. Okay, so this is qv, right? Then once I know this, I can use the Biot Savarts law over here already. So the magnetic field created by IDL at point P is what? I'm running out of ink, so I need to get a new pen. Okay, yeah, this one got ink. So the magnetic field created by this is Well, we are looking at an infinitesimal piece, right? So infinitesimal piece is created by using my Biot Savarts law. And well, we haven't called it Biot Savarts law yet. Using this equation. So this is the charge V and then the R hat, right? So R hat was this R hat and then divided by R square. Okay, so yeah, right, and from this equation, right, so we have, since this dqv is equals to idl, then my infinitesimal magnetic field created by this segment is just idl cross r hat and then dividing by r square. So therefore my total magnetic field at P, right? So we're just focusing on a specific point P. So this segment will create dB, right? Because I know the charge here, I know the drift velocity at this point, and then I know everything. So I know the distance is R, right? So this is one segment will contribute dB. So other segment will contribute all the other dB. So the total magnetic field is just the integral of all the magnetic field created by all the segments. So it's basically just integral of all this. Right, so I got IDL cross R hat dividing by R square. Okay, so therefore finally we get the formula for my magnetic field is just, these are constant. So this is constant. So constant, no need to integrate. The current may or may not be a constant. It depends on the question. So just to be safe, we will keep it inside first. But don't worry, you will see for most of the examples, this expression will simplify a lot. The integral just looks scary right now because it's a general formula. It's supposed to adapt to different situations, right? But in any case, we have found this formula of the magnetic field created by a wire. And this is what we call the Biot Savarts law. Okay. Yeah, imagine Judge Dredd saying, or Biot Savarts wearing Judge Dredd helmet saying, "This is my law." Okay. So it's a magnetic field created by this piece of wire. What are you guys talking about? Okay. Something you guys deleted. But yeah, so this is the Biot Savarts law, and I guess this is as far as we should go for now, because we are kind of out of time already. And also, yeah, not to over... So how to use the Biot Savarts law is a bit more math. So I guess it is a good place to leave it until after the midterm exam to start making use of this equation. Okay. So yeah, that should be all for today. The next thing is going to be the exam already. So Wednesday is a public holiday, no class. The exam is on Thursday, what was it, 4 to 6 p.m. right? So yeah, don't forget the exam, don't be late, and all those things.